Every spacecraft humanity has ever launched would eventually die if it left the solar system forever. Not because it ran out of fuel, not because it wandered into some wall at the edge of the universe. It would die because something inside it would break, and no one would be coming to fix it. The International Space Station is the most complex structure humanity has ever assembled and placed in orbit. It has been continuously occupied since the year 2000. It has hosted hundreds of astronauts from more than a dozen nations. It is a genuine triumph of international engineering, and it would be dead within a few years if the resupply mission stopped. Dead if the software patches stopped arriving. Dead if the replacement parts stopped showing up on cargo vehicles. Dead if the hundreds of engineers watching every sensor reading around the clock stopped watching and responding. The station works because Earth is 400 kilometers below it, always available, always capable of sending help. Move that station past Mars and the help disappears. Move it past Jupiter and the help is a memory. Move it out past the edge of the heliosphere, out past where Voyager 1 finally crossed into interstellar space after 35 years of travel, and the help is not merely unavailable, it is conceptually impossible. A radio signal takes more than 22 hours to reach Voyager 1 right now. A resupply mission to interstellar space would take decades to build and centuries to arrive. A rescue is not delayed. A rescue does not exist. A real Starship, a machine designed to carry human beings between star systems, would have to do everything the International Space Station does, without a single one of those lifelines. No resupply, no rotating crews returning to Earth, no software updates from mission control, no spare parts from any factory on any planet. Everything required to survive the voyage must be aboard at departure, or manufactured aboard during the voyage, or the mission fails. Not fails in the bureaucratic sense of missing a deadline, fails in the sense that the people inside die, somewhere between stars, with no one able to reach them. This is what interstellar travel actually demands, and it is almost never the part of the conversation that gets the attention it deserves. The engines get the attention, the fuel calculations get the attention, the question of how fast the ship can go gets all the enthusiasm, but speed is not the primary enemy of an interstellar mission. Time is the enemy, and time attacks every system aboard the ship simultaneously, without pause, without mercy, without any interest in how elegantly the engineering was done or how much money it cost to build. By the end of tonight, you will understand why a real Starship is not a faster rocket. It is something far harder than that. And the reason it is harder is sitting in engineering databases and materials science literature and medical research journals that already exist. The data is there. It is simply not the part of the story that usually gets told. If this kind of deep engineering reality is what you come here for, hit the like and subscribe. It genuinely helps this channel reach more people who want the honest version of these conversations. Now, let's begin. Think about the longest any real machine has ever operated without human hands touching it for maintenance. Not a monument carved from stone, not a satellite drifting in a perfectly stable orbit with no fluids flowing and no moving components wearing against each other. A real machine with fluids and pumps and electronics and actuators cycling continuously every second of every day. Voyager 1 is the honest answer. Launched in 1977, it is still transmitting faint signals from interstellar space nearly 5 decades later. More than 160 astronomical units from the Sun, moving at about 17 kilometers per second through the space between star systems. It is the most distant human-made object that has ever existed. And it is the size of a small car. It carries no crew, no atmosphere, no water, no food. Its radioisotope thermoelectric generators originally produced about 470 watts, and have been losing roughly 4 watts per year since launch, which means the power available now is barely enough to keep the transmitter running. Engineers have already powered down most scientific instruments to stretch that budget. Several thruster clusters have degraded enough that backup systems never designed for primary use are now doing primary work. A radio command sent to Voyager 1 today takes more than 22 hours to arrive. The confirmation that it worked takes another 22 hours to come back. Every interaction is sent blind into a communications round trip that spans nearly 2 days. Voyager 1 is the most successful long-duration deep space machine humanity has ever built, and it is an almost inconceivably simple object compared to what a crude interstellar vessel would require. Now scale the complexity upward by a factor that is difficult to express with any number. A real Starship is not a probe, it is not a capsule, it is not a vehicle, in any sense the word normally implies, where vehicles draw from infrastructure at both ends of their route. A real Starship is a sealed world. Its only supply base is itself. Define it precisely. A starship is a spacecraft designed to carry human beings across interstellar space for a duration long enough to reach, meaningfully study, and potentially inhabit another stellar system. Every word in that definition conceals an engineering crisis. Carry human beings means a closed-loop life support system that works for the full duration without any external input. Interstellar space means a radiation environment, a navigation challenge, and a communication delay that has no analog in any mission ever flown. Duration long enough to reach means years at minimum, decades more likely, centuries for any target beyond the few nearest stars, at any velocity, even theoretically achievable with known physics. Meaningfully study means the instruments must still function at arrival, after decades or centuries of degradation. Potentially inhabit means the ship must carry not just the crew, but the agricultural, medical, manufacturing, and institutional infrastructure required to sustain a viable long-term presence, somewhere with no existing support structure of any kind. Strip any one of those requirements away, and you do not have a starship. You have a probe, a flyby vehicle, or a coffin with momentum. A machine that is moving in the right direction, but is no longer capable of what a starship is supposed to do. The International Space Station is the honest baseline. 25 years of continuous human occupation. Multiple resupply missions per year delivering food, water, clothing, spare parts, and equipment. Rotating crews arriving fresh from Earth every 6 months, replacing colleagues who return home for medical evaluation and recovery. Hundreds of ground engineers monitoring every sensor in real time. The proximity to Earth's entire industrial base as a backstop against any failure mode the designers did not fully anticipate. And even with every one of those supports, the station's life support systems require constant hands-on attention. Carbon dioxide removal assemblies fail and need component replacement. Water recovery membranes reach end of life and must be swapped out. Oxygen generation hardware needs servicing. Coolant loops develop slow leaks that take weeks of methodical work to trace and repair. The systems work because the support is constant. A real starship must do everything the station does, plus accelerate itself across light years, plus grow its own food, plus shield its crew from radiation far beyond anything inside Earth's magnetosphere, plus manufacture replacement parts for components that wear out, plus provide medical care equivalent to a small hospital, plus close its water loop to something approaching 100% recovery, plus navigate without ground-based tracking, plus manage all of the social and psychological and institutional challenges of a human community sealed inside metal for longer than most nations in human history have managed to exist. And it must do all of that with nothing arriving from outside the hull, ever. That is the machine this conversation is about. There is a ladder of difficulty in human spaceflight, and most conversations about starships skip most of its rungs. Understanding what each rung actually demands is the only way to see why the step interstellar travel is not a step up the same ladder. It is a jump to a different ladder entirely. Low Earth orbit is the bottom rung. You are 400 kilometers above the surface. A return to the planet takes hours. Communication delay with the ground is a fraction of a second. Resupply missions take weeks to arrange and reliably arrive. The station sits inside Earth's magnetosphere, which absorbs most of the incoming charged particle radiation from solar events and from galactic sources. The engineering challenges are serious and well-studied and bounded. Humanity has maintained continuous human presence in low Earth orbit since November of 2000. We know how to do this. The moon is the next rung. Communication delay is barely a second in each direction, barely enough to notice in a conversation. Resupply is expensive but achievable. Radiation exposure increases meaningfully since lunar missions venture outside the magnetosphere, but the moon is close enough that realistic abort scenarios exist for most failure categories. If something goes critically wrong on the surface, the crew can potentially come home within days. The moon is hard. It is not Mars hard. Mars changes the fundamental character of the problem. At closest approach, Mars sits around 55 million kilometers from Earth. At greatest separation, that distance exceeds 400 million kilometers. Communication delay ranges from about 4 minutes to more than 24 minutes each direction, meaning a back-and-forth exchange with mission control can consume close to an hour. A crewed Mars mission requires roughly 2 to 3 years from launch to return, paced by orbital mechanics. The crew must carry or produce essentially everything required for the entire duration. Radiation exposure during the interplanetary transit is substantial and cumulative, building over months with no planetary magnetic field to reduce it. Medical emergencies cannot be evacuated. Mars introduces the concept of no rescue as an operational reality rather than a theoretical edge case. But even Mars is inside the solar system. The sun is still a usable power source at Mars distance. decades. Communication with Earth, while painful, still functions. The journey measures in months. The crew knows they are coming home. Beyond the heliosphere, that entire support structure collapses. The sun shrinks to a point of light. Solar panels are useless. Communication operates on delays measured in years. The radiation environment transitions from the intermittent hazard of solar particle events to the permanent, omnidirectional, unceasing bombardment of galactic cosmic rays. The duration of even the shortest plausible interstellar voyage is measured in decades, and for realistic velocities achievable with known physics, in centuries. The gap between Mars and interstellar space is not one step up the same ladder. It is the difference between a serious engineering challenge supported by the full industrial capacity of civilization and a problem that requires that industrial capacity to somehow fit inside a single sealed hull for the rest of the mission's operational lifetime. A starship breathes, not biologically, mechanically, in a way that is just as fragile and just as lethal when it stops. Every habitat containing human beings must continuously remove the carbon dioxide produced by each exhalation, replenish the oxygen consumed by each breath, and scrub the accumulating trace contaminants from skin oils, equipment, outgassing, food processing, and every polymer surface in the structure. The International Space Station manages this through a network of chemical scrubbers, electrolysis units, catalytic oxidizers, and trace contaminant control assemblies. It works because every component that degrades or fails is replaced with parts delivered from the planet below. The carbon dioxide removal assemblies on the station use molecular sieve beds that absorb CO2 and release it during regeneration cycles. Those beds degrade under repeated thermal cycling. Their molecular structure changes over time, and efficiency decreases. On the station, degraded beds are replaced with fresh material arriving on cargo flights. On a Starship, replacement material must either be manufactured aboard from raw stock carried at departure, or the crew must find a way to restore the existing beds to function. If neither is possible, CO2 levels in the cabin begin to climb. The physiological effects of elevated CO2 are well established and begin far below what most people assume. At around 1% atmospheric concentration, crew members experience persistent headaches and find sustained concentration difficult. At 2%, measurable cognitive impairment appears, affecting decision-making and response time. At 5%, symptoms become severe. The margin between a functioning scrubber system and a life-threatening atmosphere can be as small as a sorbent bed operating at 80% of its original efficiency instead of 100%. Oxygen generation mirrors the problem through electrolysis, splitting water into hydrogen and oxygen using electrical current, then combining the hydrogen with CO2 in a Sabatier reactor to produce water and methane, partially closing the chemical loop. Electrolysis cells corrode, catalytic beds accumulate contaminants and lose activity. The hardware requires maintenance, and the materials required for that maintenance must exist somewhere aboard. Every polymer surface inside the ship outgasses trace quantities of solvents, plasticizers, and decomposition products. Human metabolism produces hydrogen, methane, and dozens of other minor volatile compounds. Cooking releases additional compounds. The trace contaminant control system manages these through activated carbon beds and catalytic oxidizers. Those beds reach saturation. If replacement material is unavailable and no regeneration method is viable, contaminant concentrations in the cabin atmosphere rise slowly, producing chronic exposure effects that develop over months before anyone connects the symptoms to the source. The air aboard a Starship is not a static resource loaded at departure and left alone. It is a dynamic chemical equilibrium maintained continuously by machinery. Every breath the crew takes shifts that equilibrium away from habitability. The machinery pushes it back with every operating cycle. If the machinery slows or loses efficiency, the equilibrium drifts. In a sealed vessel in interstellar space, there is no outside air to dilute the drift. The atmosphere is either maintained or the crew dies. There is no recoverable middle ground. Water is not simply a consumable aboard a Starship. It is a structural element of survival that underlies multiple independent critical systems simultaneously. Every molecule of water the ship carries at departure represents the total possible supply for the entire voyage, because no water exists anywhere between star systems at any density that could be collected. A person needs roughly 2.5 to 3 liters of drinking water per day under typical conditions. Physical labor, elevated cabin temperatures, or illness increases that requirement. Add food preparation, basic hygiene, and agricultural irrigation for food production systems, and the daily per-person water demand rises substantially. For a crew of 100 over a 50-year voyage, the cumulative water requirement is millions of liters. Carrying that volume from departure as stored mass is physically impossible within any realistic ship design. The mass alone would prevent the ship from ever achieving meaningful velocity. The solution is closed-loop water recovery, reclaiming every possible molecule from crew urine, humidity condensate from the cabin atmosphere, wash water, water produced by the Sabatier reactor, and agricultural transpiration. The International Space Station's water recovery system now achieves closure rates approaching 98%. That remaining 2% arrives on resupply missions. On a Starship, that 2% is simply gone, permanently. Over a 50-year voyage, the cumulative loss from a 98% system represents a significant fraction of the starting inventory. And 98% is not a stable long-term number. It is a snapshot of performance when the system is well maintained. Filter membranes foul over time and lose permeability, requiring higher pump pressures to maintain flow rates, which stresses other components. Catalytic oxidation stages lose activity as contaminants accumulate on active surfaces. Ion exchange resins reach saturation. Distillation surfaces develop mineral scaling. Every degradation pathway lowers the effective recovery rate, which accelerates the depletion of the ship's water inventory. A Starship's water recovery system must approach 100% closure for the full duration. No closed-loop water system built by human beings has ever demonstrated anything approaching that standard for even a fraction of the time an interstellar mission would require. Water is also feedstock for electrolysis to produce oxygen. It is the cooling medium in thermal management loops. It is a component of hydroponic nutrient solutions. In some proposed ship designs, it is a radiation shielding material in water-filled walls around the crew habitat. Lose the water inventory below a critical threshold, and multiple independent survival systems begin failing simultaneously. The failure is not linear. It is a cascade, because water is the common dependency beneath several critical functions that otherwise appear unrelated. The mathematics of feeding a crew for an interstellar voyage eliminates carrying everything from departure within a few minutes of calculation. A crew of 100, consuming 2,000 calories per person per day, needs over 3.6 billion calories across a 50-year voyage. Converted to optimized freeze-dried provisions, that mass runs into hundreds of metric tons. That mass must be accelerated to interstellar velocity with the rest of the ship, which compounds the propulsion requirements in ways that rapidly make the purely stored food approach physically impossible for any mission beyond a few decades. The unavoidable response is bioregenerative food production, growing food aboard the ship using closed-loop agricultural systems powered by artificial lighting. This offers multiple benefits. Plants absorb CO2 and release oxygen, contributing to atmospheric management. They transpire water that can be recovered as condensate. They produce genuine psychological benefits in an environment where access to living organisms and something resembling natural space matters for crew mental health over the very long term. But plant growth in a closed, isolated, low-gravity or rotating artificial gravity environment does not behave exactly like plant growth in a field on Earth. And the engineering of bioregenerative agriculture at crew-sustaining scale is substantially harder than the small-scale experiments conducted in orbital environments so far suggest. Root zone management in microgravity is complex. Plants use gravity as a directional reference for root orientation, and without that reference, nutrient delivery and water management in the root zone requires active engineering solutions. Pollination must be managed manually or mechanically, since wind and insect pollinators either do not exist or must be carefully maintained aboard. Pest management in a closed agricultural system with no natural predator ecology and no external fields to rotate into is a vulnerability with no comfortable solution. A fungal outbreak or insect infestation can spread through an enclosed bay far faster than through an open field, with nothing to stop it except the crew's intervention and whatever materials are aboard. Plant genetics will drift over generations. Agricultural varieties are optimized for performance under specific conditions. Growing continuously in the unique closed environment of a starship, subject to the ship's specific radiation levels, atmospheric composition, lighting spectrum, and microbial ecology, natural selection will begin favoring traits that are advantageous in that environment, which may not be the traits that were optimized for caloric yield and nutritional density at departure. Without access to external seed banks and without the ability to introduce genetic diversity from outside, the ship's crop varieties will slowly evolve away from what was planted. Nutritional completeness over multi-decade timescales is an under-examined vulnerability. A diet that meets macronutrient requirements but is subtly deficient in specific micronutrients or essential fatty acids produces health effects that develop over years rather than weeks. A crew that is not starving may still develop deficiency conditions that impair their capacity to maintain the ship. The relationship between diet, gut microbiome, and long-term human health in a sealed, isolated environment with a unique microbial ecology is not fully characterized by any research program in existence. A starship's agricultural system is not a farm in any ordinary sense. It is a biological machine that must produce a specific caloric and nutritional output every day for the full voyage from inputs that are all themselves part of closed loops that interact with each other and with the crew. A sustained failure in any one of those interdependencies triggers a food shortage that takes months to recover from, during which the crew draws from finite stored reserves that cannot be replenished from any external source. Inside Earth's magnetosphere, the radiation environment is manageable. Outside it, in interplanetary space, solar particle events become a periodic hazard that can be partially managed through monitoring and sheltering. In interstellar space, beyond the heliosphere's protection entirely, the dominant radiation source becomes galactic cosmic rays, and galactic cosmic rays never stop. Galactic cosmic rays are high-energy particles accelerated to energies measured in billions to trillions of electron volts per nucleon by supernovae, pulsar winds, and other violent astrophysical processes distributed across the galaxy. They include protons, helium nuclei, and fully stripped heavy ions of elements like iron and silicon. They arrive from every direction simultaneously. They have no solar cycle, no warning period, no predictable burst structure. They are a permanent feature of the interstellar environment, present equally every second of every year of the voyage. The biological damage from galactic cosmic rays is not simply proportional to the total energy deposited in tissue. Heavy ion cosmic rays produce what physicists call high LET radiation, meaning they deposit their energy along an extremely dense, narrow track through biological material. A single iron nucleus traveling at a significant fraction of the speed of light can shatter both strands of a DNA double helix along its entire track through a cell nucleus, producing damage that the cell's repair mechanisms cannot correctly address. These double-strand breaks in the densely ionized pattern of heavy cosmic ray tracks produce chromosomal rearrangements and deletions at a rate that light radiation of equivalent total energy does not, because the repair enzymes are overwhelmed locally by the density of damage. Passive shielding helps, but only up to a point. Adding mass between the crew and incoming cosmic rays does reduce the primary particle flux. But cosmic ray particles at interstellar space energies interact with the nuclei of shielding atoms and produce secondary particles through nuclear spallation. Neutrons, protons, lighter nuclear fragments, and gamma rays that can spread out from the primary track and irradiate a larger volume than the original ion alone would have reached. Beyond an optimal shielding thickness that depends on the material, adding more shielding material actually increases the effective biological dose inside the habitat, because the secondary radiation from the additional material outweighs the attenuation benefit. Hydrogen-rich materials like polyethylene are preferred over metals because lighter nuclei produce fewer energetic secondary particles. But even with the most optimized passive shielding a realistic ship design could carry, the annual galactic cosmic ray dose in interstellar space would exceed the lifetime career limits established by major space agencies within a few years of departure. Active electromagnetic shielding, using superconducting magnets to deflect incoming charged particles, has legitimate physics behind it and represents the only approach with meaningful potential to actually protect crew members over multi-decade timescales. But it has not been demonstrated at any relevant scale. It requires enormous continuous power, continuous cryogenic cooling to maintain superconductivity, and reliable operation for the full voyage duration. And it provides no protection against neutral particles like neutrons produced by spallation reactions in the hull, since neutral particles follow straight paths through magnetic fields, unchanged. The consequence for the crew is not a dramatic acute radiation event. It is a slow, grinding accumulation of biological damage across the full duration of the voyage. Cancer rates climb, cataract formation accelerates, cardiovascular disease risk increases. Cognitive function may subtly degrade in some crew members over years. The people responsible for maintaining the ship become progressively more biologically fragile at exactly the point in the mission when they have the least access to medical support, the smallest possible pharmacological inventory, and no ability to transfer patients to any higher level of care. Every system described in this conversation requires electrical power to function. The atmospheric scrubbers need it. The water recovery membranes need it for pumps and distillation heating. The electrolysis system that produces oxygen needs substantial continuous power. The agricultural lighting that drives photosynthesis is the single most energy-intensive component of any bioregenerative life support system. The navigation computers need it. The communication systems need it. The fabrication equipment needs it. The medical systems need it. Active radiation shielding, if any is implemented, requires enormous continuous electrical power, and the propulsion system, at departure and arrival, requires far more power than any other system aboard. In the inner solar system, power comes from the sun. At Earth's orbital distance, solar panels receive about 1,360 watts per square meter. At Jupiter, that falls to roughly 50 watts. At Saturn, below 15. Beyond Saturn, solar energy is insufficient for anything more demanding than a small probe's basic housekeeping. In interstellar space, there is no usable solar energy at all. Radioisotope thermoelectric generators have proven themselves as long-duration deep space power sources. The Voyager probes have relied on them for nearly 50 years. They have no moving parts, require no maintenance, and operate silently and continuously from radioactive decay. But their power output is measured in hundreds of watts and declines steadily as the fuel decays. A Starship requiring kilowatts or megawatts of continuous power to sustain all its life support systems, food production, active shielding, and navigation needs something orders of magnitude more powerful. Nuclear fission reactors are the only proven path to that level of electrical output without access to sunlight. Compact space-rated designs have been tested at small scales. The physics of fission are well understood, and the energy density of enriched uranium fuel is extraordinary. But a reactor designed to power an interstellar starship must operate without meaningful maintenance for decades or centuries in an environment where every replacement of a component is either a fabrication challenge or impossible. Fuel elements must maintain structural integrity under continuous neutron bombardment. Coolant loops must circulate without pump replacement. Control mechanisms must function reliably in a radiation environment that degrades the electronics on which modern reactor control systems depend. The longest operating commercial fission reactors have been running for roughly half a century, and every one of them is maintained by a specialized industry with access to global supply chains. A reactor that must operate for a century without any external maintenance intervention is beyond current engineering experience. Nuclear fusion would theoretically provide even more energy per unit fuel mass with different byproduct concerns. But controlled sustained fusion has not been demonstrated at net positive energy output, despite more than 7 decades of research investment. Claiming that a Starship will run on fusion is a claim about the future performance of a technology that has consistently defied optimistic timeline predictions throughout the entire history of the space age. It may arrive. It has not arrived yet. Lose power aboard a Starship, and you do not lose one system. You lose all of them simultaneously. Power is not one survival factor among several. It is the one survival factor that all others depend on. The failure mode of a power system that slowly loses capacity over decades is not a sudden blackout. It is a years-long triage, a slow process of deciding which systems continue running at full capacity and which begin operating at reduced load, which scientific instruments get powered off, which agricultural bays lose lighting, which crew quarters fall below comfortable temperature, which repair operations get postponed for lack of power to run the fabrication equipment. The ship slowly becomes less capable of being the world it needs to be, in a spiral that is difficult to reverse once it begins. Every mechanical component aboard a Starship has a finite operational lifespan. Bearings wear, seals degrade, pump impellers erode, valve seats corrode. Electrical insulation becomes brittle under years of radiation exposure. Circuit boards accumulate damage from cosmic ray hits. Solder joints fatigue under thermal cycling. Lubricants break down chemically over time and lose viscosity. Cable insulation develops micro cracks that propagate toward short circuits. Every one of these failures can be predicted in a statistical sense. Engineers can estimate mean time between failures for most standard components. Stocking spare parts for every possible failure over a 50-year voyage, let alone a 200-year or 400-year one, rapidly becomes a mass problem that overwhelms any reasonable ship design. Every kilogram of spare parts is a kilogram that must be accelerated to interstellar velocity, which increases the fuel requirement, which increases the propulsion system mass, which requires more structural support, which adds more mass, in a compounding spiral that sets hard limits on how much spare parts inventory any real ship design can carry. Three-dimensional printing and additive manufacturing offer a partial solution. If the ship carries sufficient raw material feedstock, metal powders, polymer filaments, ceramic precursors, a capable fabrication system could manufacture replacement parts on demand throughout the voyage. But additive manufacturing is not magic. Current technology can produce functional parts across a range of materials, but achieving the metallurgical properties required for high-stress, high-temperature rotating components remains genuinely difficult. Printed metal parts often have different grain structures, different porosity distributions, and different fatigue characteristics compared to conventionally forged or machined counterparts. A replacement bearing that looks dimensionally identical to the original, but fatigues to failure in 1/10 the operational hours, creates a cascading maintenance burden that accelerates the ship's overall degradation faster than the original failure would have. Fabrication also requires expertise. Someone aboard must understand how to design the replacement component, select the appropriate feedstock material, configure the process parameters for that material, post-process the resulting part to achieve required surface finishes and heat treatment states, inspect it for defects using whatever non-destructive evaluation equipment is available, and install it correctly. That knowledge must be actively maintained and transmitted from one generation of crew to the next. If the fabrication specialist is lost to accident or illness, and their successor received incomplete training, the ship's manufacturing capability is degraded, and every component that subsequently fails becomes a permanent loss rather than a maintenance event. The spare parts problem interacts with the fabrication problem in a particularly insidious way. Fabricating replacement parts consumes raw material feedstock. That feedstock is finite and cannot be replenished. A ship that begins its voyage with a 10-year supply of fabrication feedstock has a 10-year manufacturing window, after which every component failure becomes either a creative salvage exercise or a permanent loss of capability. Managing that feedstock across the full voyage duration is itself an engineering and logistics problem that receives almost no attention in most discussions of interstellar mission design. The maintenance chain is not a single system. It is the interconnected network of expertise, tools, materials, and institutional knowledge that allows one generation to hand off a functioning ship to the next. Every link in that chain must be preserved. A ship where the fourth generation of crew is slightly less trained than the third, who were slightly less trained than the second, enters a generational decay of institutional competence that is nearly impossible to detect until something fails that the current generation cannot fix. The interstellar medium is not a perfect vacuum. It contains roughly 1 atom per cubic centimeter on average, mostly hydrogen, along with scattered dust particles of varying composition and size. At low velocities, dust encounters are inconsequential. A dust grain at relative rest barely registers as a threat to any reasonable structure. At a significant fraction of the speed of light, every particle of interstellar dust becomes a hypervelocity projectile. A single dust grain with a mass of 1 microgram, striking a hull at 5% of the speed of light, carries kinetic energy comparable to a rifle bullet. At 10% of light speed, that energy scales with the square of velocity and enters the range of small explosive charges. Over a voyage lasting decades, the forward-facing surfaces of a starship would absorb an enormous number of such impacts, not simultaneously, but continuously. Each impact erodes shielding material, pits structural surfaces, damages external sensor arrays, and weakens the hull's ability to contain atmosphere and resist subsequent impacts. The engineering response to orbital debris impacts in low Earth orbit involves Whipple shields, multi-layered barriers with a thin sacrificial outer wall designed to vaporize incoming particles before they can reach the pressure hull as solid fragments. The physics of hypervelocity impacts at orbital velocities, roughly 10 to 15 kilometers per second, are reasonably well understood and have been tested extensively. At the velocities required for interstellar transit, thousands of kilometers per second, the physics change dramatically. At those relative velocities, both the incoming particle and the shield material vaporize and produce plasma jets with different penetration characteristics than solid fragments. The shielding design principles validated for orbital velocities do not straightforwardly transfer to interstellar velocities, and the experimental data required to validate new designs does not exist. The cumulative erosion of forward-facing surfaces over decades of continuous bombardment is a design constraint that has no precedent in any spacecraft ever built. Shielding material that is adequate at departure may be eroded to below minimum effective thickness years before arrival. The hull beneath may begin receiving elevated particle flux through thinned areas before anyone is aware the erosion has progressed that far. External sensor arrays, communication dishes, and any active component on the ship's forward face must either be designed to survive this erosion or be protected behind sacrificial shields, which themselves erode and must somehow be replenished or replaced from inside the ship without the option of an external spacewalk, in conditions where the interstellar medium itself poses a radiation hazard. There is also the matter of individual high-energy micrometeorites, objects larger than typical interstellar dust but smaller than detectable hazards. A pebble-sized object struck at 5% of light speed would release energy comparable to a substantial explosive charge. These impacts may be rare over a 50-year voyage, or they may not be rare at all depending on the specific trajectory through the interstellar medium. The distribution of small solid objects in interstellar space is not well characterized. There is no survey of the interstellar medium at the spatial resolution required to know what specific regions the ship will be traversing. A crewed starship carries, by definition, a small sealed population that cannot be evacuated, cannot be reinforced, and cannot receive any material or expertise from outside the hull. Medical care for that population must be provided by whoever aboard has the most relevant training, using whatever equipment and medications exist at that moment in the ship's inventory for every health event that occurs across the full voyage. Modern medicine is not self-contained. It is deeply embedded in a support infrastructure that most people never think about. A patient requiring emergency surgery is treated in a facility with sterile operating theaters, specialized equipment, a trained anesthesiologist, surgical nurses, pathology and radiology services, a pharmacy within access to the full spectrum of pharmaceutical options, and a surgical team that can call in additional specialists if the case develops unexpected complications. The entire system is backed by a global supply chain that delivers specific drugs, specific implants, specific equipment in days. A starship has none of that infrastructure. The surgical space may double as a laboratory on every non-emergency day. The person providing anesthesia may also be the ship's primary mechanical engineer who spent the morning repairing a coolant pump. Surgical instruments are finite and must be sterilized using equipment that itself requires maintenance and consumables. The pharmaceutical inventory is fixed at departure and subject to degradation from the moment the ship leaves the system. Pharmaceutical degradation in the space environment is more severe than the expiration dates printed on terrestrial medications imply. Those dates are established under controlled storage conditions on Earth, typically room temperature and low humidity, over periods of 2 to 5 years. A starship's pharmaceutical inventory faces continuous radiation exposure, temperature fluctuations from thermal management cycles, and humidity variation from the recycled atmosphere. These conditions accelerate the chemical breakdown of complex organic molecules in ways that standard stability testing does not characterize. Antibiotics in the beta-lactam family, the penicillins and cephalosporins that cover a wide range of bacterial infections, can lose more than half their potency within 3 to 4 years, even under reasonably controlled conditions. Epinephrine, the first-line treatment for anaphylactic shock and cardiac arrest, degrades predictably within about 2 years. Insulin, essential for any diabetic crew member, is temperature-sensitive and cannot be stored reliably for years without precisely controlled refrigeration. Pain medications, anticoagulants, cardiac drugs, and the vast majority of the pharmacopoeia have stability limitations that make maintaining an effective medical inventory across a multi-decade voyage a fundamental challenge. Cancer treatment is the particular pharmaceutical nightmare of an irradiated crew. Given the elevated galactic cosmic ray dose, cancer incidence among the crew will almost certainly be higher than in any Earth population. The drugs used to treat the most common radiation-induced cancers, alkylating agents, platinum compounds, antimetabolites, topoisomerase inhibitors, are among the most chemically unstable medications in clinical practice. Many require reconstitution from powder immediately before administration, with the powders themselves having limited shelf lives and the reconstituted solutions having shelf lives measured in hours. The sterile water required for reconstitution must come from the ship's recycled supply. The sterility of that supply, while maintained to the best of the ship's capability, will not match the standards of a pharmaceutical manufacturing facility on Earth. A crew facing elevated cancer rates may discover that its treatment inventory is expired, degraded, or exhausted from treating previous patients in earlier decades. The medical system is not simply a set of equipment. It is a set of capabilities that must be sustained through maintained equipment, sufficient and pharmacologically active medications, and trained personnel, all of which degrade independently over the voyage in ways that compound each other. In the inner solar system, a spacecraft fixes its position using the sun, the planets, and ground-based tracking stations that measure the spacecraft's radio signal with extraordinary precision. The Deep Space Network can determine the position of a distant spacecraft to within a few kilometers using very long baseline interferometry techniques. In interstellar space, none of this infrastructure exists. There are no tracking stations. There is no sun to serve as a primary reference. Navigation depends entirely on the ship's own optical instruments, measuring the angular positions of distant stars and comparing those measurements against a stored catalog. This sounds straightforward, but conceals a growing problem. As the ship moves through interstellar space, the apparent positions of nearby stars change due to parallax, the same phenomenon that allows depth perception in human vision. A star at a distance of 5 light-years shifts its apparent position measurably as the ship moves across a baseline of 1 light-year. The stellar catalog carried at departure must account for these parallax shifts as a function of the ship's displacement from the solar system. For nearby stars, the parallax calculation is manageable if the star's distance is known precisely. But stellar distances are not all known to equal precision, and distance measurement errors propagate into navigation errors. Additionally, stars are not stationary. They move through the galaxy on their own orbits. This proper motion, typically measured in arcseconds per year from Earth, accumulates over decades and centuries of transit time into angular offsets that can substantially change a star's apparent position from what the departure era catalog predicts. The proper motion of nearby stars is measured with varying degrees of precision. A navigation system relying on reference stars, whose proper motions are only approximately characterized, accumulates a navigation error that grows with the voyage duration. The instruments that observe the reference stars are themselves degrading. Optical detectors accumulate radiation damage, with individual pixels developing permanently elevated noise or going completely dark. The optical surfaces of telescopes and star trackers develop micro-pitting from interstellar dust impacts and molecular contamination from slow outgassing within the instrument housing. Each degradation mode introduces systematic errors that shift apparent stellar positions by tiny but accumulating amounts. Without an external calibration reference, the crew cannot easily distinguish between a genuine navigational drift and a sensor artifact from a degraded detector. A ship that has drifted 1% off course from navigational error accumulates a position error of roughly 1/10 of a light year over a 10 light year voyage. 1/10 of a light year is approximately 9.5 trillion kilometers. A ship that arrives at that position, looking for a destination star system, may not find the system easily because the angular offset from the intended approach direction is large enough that the target system might not be within the instrument's field of view. The ship must search. Searching consumes time and power. The deceleration burn, if it was designed to occur at a specific point along the approach trajectory, may need to be modified, and every modification draws on propulsion system reserves that were calculated against an ideal trajectory, not a search trajectory. The computing infrastructure of a starship must manage navigation calculations, monitor all life support systems, control the propulsion systems at departure and arrival, process scientific instruments, maintain communication systems, and handle crew-facing applications from medical diagnosis software to the ship's educational databases. It must do all of this continuously for the full voyage duration in an environment where the radiation flux is substantially higher than anything any computer system has previously been asked to operate in for extended periods. Galactic cosmic rays cause single-event upsets in semiconductor devices, events where a high-energy particle strikes a transistor and deposits enough charge to flip the bit stored in that transistor, changing a stored value without triggering any apparent fault. In low Earth orbit inside the magnetosphere, single-event upsets are relatively rare and are managed through error-correcting memory and redundant processing paths. In interstellar space, where the galactic cosmic ray flux is roughly twice the rate inside the heliosphere, the frequency of single-event upsets is meaningfully higher and continuous. Most individual bit flips in memory are caught and corrected by error-correcting codes before they cause visible system problems. But error correction is not perfect. Some errors occur in the wrong location at the wrong time and slip through. Others accumulate in ways that error correction cannot detect, slowly corrupting stored values in databases, navigation catalogs, system configuration files, and engineering drawings. Over decades, the accumulated effect of cosmic ray interactions in semiconductor devices degrades their performance. Transistors become leakier as radiation damage creates new conduction paths through their gate oxides. Threshold voltages shift. Clock speeds must be reduced to maintain logical stability. Storage media accumulate undetectable errors at rates that eventually compromise data integrity. The computing systems most critical to a starship must operate reliably for decades in this environment. No computing system has ever been subjected to this radiation environment for this duration. Modern semiconductor processes that achieve extraordinary capability in benign environments are often less radiation tolerant than older processes, because the design features that enable high density and high performance also create greater vulnerability to radiation-induced charge deposition. Radiation-hardened processors exist and are used in space applications, but they sacrifice performance relative to commercial equivalents by significant margins. And even radiation-hardened designs have been qualified only to radiation environments and time periods far shorter than an interstellar mission would require. The software running on these systems is an additional vulnerability. Software that operates correctly at departure may develop bugs that only manifest after specific sequences of events that arise years later. In the mission environment, with no access to software updates from Earth and no ability to bring in outside expertise, the crew must be capable of diagnosing and correcting software defects in complex systems using only the documentation and expertise they carry. The institutional knowledge required to maintain and repair complex software systems across decades, including the knowledge of what the software was originally designed to do and how its design was intended to work, must be actively preserved and transmitted from one generation of crew to the next. Many interstellar mission architectures envision a structure with three distinct propulsion phases: a high-thrust acceleration burn at departure that achieves cruise velocity, a long coast phase during which the ship travels at constant speed through interstellar space, and a high-thrust deceleration burn at arrival that slows the ship enough to enter the destination system. The deceleration burn requires roughly as much energy and propulsive capability as the original acceleration. The ship must essentially fight the same battle at arrival that it fought at departure. Between those phases, the propulsion system sits dormant, not idle in the sense of a running engine at low power, but actually cold and inactive for years or decades, depending on the voyage length. Mechanical and chemical systems do not survive long dormancy without degradation, and the degradation accumulates invisibly in silence, without triggering any monitoring system, manifesting only when the dormant system is finally commanded to operate. The failure modes are well characterized in terrestrial engineering and multiply in the space environment. Residual propellant remaining in feed lines after the acceleration burn can undergo slow chemical decomposition over years, producing solid crystalline deposits that block injector orifices. If the lines are purged to prevent this, the elastomeric seals in the fuel system lose their plasticizers in hard vacuum and become brittle, developing microcracks that propagate slowly over the dormancy period and compromise pressure integrity when the system is repressurized. Turbopump bearings in a dormant system develop brinelling, the formation of small permanent depressions in the bearing race from the static load of the rotor, resting in a fixed position over years. When the pump spins up, those depressions create vibration that accelerates wear and can progress to seizure. Ignition system pyrotechnics undergo chemical aging that changes their detonation characteristics. Valve actuators develop seal embrittlement and lubricant migration. Every system that sat still while the ship coasted is a system that must prove itself functional in a single irreversible operational test at the moment when failure is most consequential. A propulsion system that performs flawlessly at departure may simply refuse to start after 50 years of cold, irradiated vacuum dormancy. There is no test fire in the middle of interstellar space. There is no way to cycle the engines periodically without expending irreplaceable propellant. The crew must trust that systems which last fired half a century ago will perform on the first command. That trust is not testable before it is needed. If the deceleration burn fails, every year of careful survival aboard the ship, every generation of crew that maintained the vessel and transmitted institutional knowledge to the next generation, every sacrifice made in the name of reaching the destination produces the same outcome as if the ship had never been built at all. The vessel flies through the destination system at interstellar velocity and continues into the void beyond. The mission is not merely incomplete, it is over. None of the failure modes described in this conversation happen in isolation. They interact, they amplify each other. They create a feedback dynamic in which each system's degradation increases the probability and severity of every other system's degradation. The result is not a linear decline in ship capability, but an accelerating spiral that is difficult to reverse once it begins and nearly impossible to reverse once it becomes established. Consider a realistic scenario. The water recovery system's filtration membranes begin losing permeability in year 18 of a 50-year voyage. Recovery efficiency drops from 98% to 91%. The crew is aware of this and begins managing the water inventory more carefully, reducing consumption for non-essential purposes. Agricultural irrigation is reduced first. Crop yields begin declining. Caloric intake per crew member falls slightly. Body mass decreases. Immune function is subtly compromised. A respiratory illness that would be a minor inconvenience for a well-nourished crew in year 5 becomes a more serious event in year 19, drawing on antibiotic reserves. Meanwhile, the reduction in hydroponic bay output has reduced the CO2 absorption contribution from the plants, placing a slightly higher load on the chemical CO2 scrubbers. The scrubbers were already operating near their design capacity. The additional load accelerates their degradation. The CO2 concentration in the cabin atmosphere begins rising slowly. The crew's cognitive function degrades at the margin, subtly and imperceptibly at first. Maintenance quality decreases slightly. A bearing in the water recovery pump that a fully alert, fully nourished maintenance technician would have caught in a routine inspection slips by unnoticed. The bearing continues to degrade. When it finally fails catastrophically in year 22, it takes with it the pump housing, requiring a fabricated replacement that is more difficult to manufacture than the bearing alone would have been. Fabrication of the replacement part consumes feedstock material and takes 2 weeks of the fabrication specialist's time. During those 2 weeks, other scheduled maintenance on the atmospheric scrubbers is deferred. Scrubber performance declines further. The cycle tightens. Each failure makes the next failure more likely, and each recovery from failure is less complete than the last. The ship does not collapse suddenly. It enters a slow, compounding erosion of margin in which every system is running slightly closer to its minimum threshold than the previous year, every repair is slightly less effective than the one before it, and the feedback between failing systems slowly amplifies in a direction that has no natural stabilizing factor. The specific scenario is invented. The dynamic it describes is not. It is the characteristic failure mode of complex closed systems operating without external support under conditions of resource depletion. It is the mechanical version of what happens to an isolated ecosystem when a key species is lost. The system reorganizes around the absence, but the reorganization is almost always at a lower level of function than before, and the loss of each subsequent element is harder to compensate for than the last. This is what interstellar travel actually demands to prevent. Not just engineering each individual system to a high standard of reliability, engineering all of them to remain above the minimum threshold simultaneously for the full duration, in an environment that degrades them all simultaneously, with resources that can only decrease over time. No human project has ever been asked to achieve that. The question of whether it is achievable at all is not settled by optimism about future technology. It is answered by the physics of degradation, the chemistry of material failure, and the mathematics of closed-loop resource management. Alpha Centauri is where every serious conversation about interstellar travel begins, because it is where the nearest stars are. The system consists of 2 sun-like stars, Alpha Centauri A and B, in a close mutual orbit, and a small red dwarf called Proxima Centauri that orbits the pair at a much larger distance. Proxima is the closest individual star to Earth at approximately 4.24 light-years. It hosts at least one confirmed roughly Earth-sized planet, Proxima b, in what is called the habitable zone. At 10% of the speed of light, a velocity roughly 3,000 times faster than any crewed spacecraft has ever traveled. The journey to Proxima Centauri takes approximately 44 years. That number sounds almost manageable. A human career, a long working life. The crew who departed might, with reasonable medical luck and radiation management, still be alive at arrival. But 44 years of continuous operation for every critical system aboard is an extraordinary engineering requirement, not a modest one. No closed-loop life support system has ever been tested for 44 years without external input. No nuclear reactor designed for spacecraft has ever operated for 44 years without a significant overhaul. No sealed human habitat has sustained crew for 44 years without resupply. The International Space Station, the longest-running crewed habitat ever built, has been continuously occupied for approximately 25 years with multiple resupply missions per year. A 44-year transit means every pump, every filter, every seal, every bearing, every circuit board aboard must either survive the entire journey or be replaced from inventory manufactured from feedstock that was loaded at departure. The spare parts manifest alone is an engineering challenge of significant complexity. How many replacement water recovery membranes are required for 44 years? How many sets of pump bearings? How many atmospheric scrubber beds? Every item added to that list increases the ship's mass, which increases the propellant required to accelerate to cruise velocity, which increases the reactor size, which increases the structural mass required to contain and shield it. The engineering trade-offs compound, and at every rung they constrain what can be carried and for how long. And then there is the destination itself. Proxima b is likely tidally locked to its host star, meaning one hemisphere faces the star permanently while the other faces permanent darkness. Habitable conditions may exist only in a narrow zone near the day-night terminator. Proxima Centauri is an active flare star that produces intense ultraviolet and particle radiation events that are orders of magnitude more powerful than anything Earth experiences from our comparatively stable Sun. These events may have stripped any atmosphere Proxima b once possessed. No confirmed detection of a Proxima b atmosphere has been made by any observational campaign to date. A crew that survives a 44-year transit may arrive at a tidally locked, heavily irradiated, atmospherically stripped rock with nothing to offer them that the ship itself cannot already provide. The engineering triumph of getting there may deliver not a new world, but a new prison with a view of a dim red star that tries to sterilize its surroundings on a regular schedule. Each star beyond Alpha Centauri on the distance ladder adds years to the transit time, and those years compound every engineering and human challenge already described. Barnard's star sits at roughly 5.96 light-years, the next individual star beyond the Alpha Centauri system. At 10% of the speed of light, the journey takes about 60 years. 60 years of mechanical operation, 60 years of radiation accumulation, 60 years of water recovery operating below its original efficiency, 60 years of food production systems slowly drifting from their designed parameters, 60 years of pharmaceutical degradation. The additional 16 years beyond Alpha Centauri are not simply additive in their difficulty. They push the survival requirements into a regime where the probability that every critical system continues functioning begins to drop meaningfully below what a reasonable engineering confidence interval would support. Barnard's star also introduces the problem of destination value. As of the most current data, no confirmed habitable planet orbits Barnard's star. Candidate signals have appeared in radial velocity surveys, but remain disputed and unconfirmed. A starship that commits 60 years of crew sacrifice to reach Barnard's star may find nothing worth the reaching. The crew arrives. Every system performed. No one died unnecessarily, and the destination contains nothing a robotic probe could not have studied more efficiently at a fraction of the cost and none of the human sacrifice. Sirius sits at approximately 8.6 light-years, making it roughly twice the distance to Alpha Centauri. At 10% of the speed of light, the journey requires about 86 years. This is the threshold where the voyage definitively spans more than one human lifetime. The crew who launched the mission will be dead before it ends. The people who arrive at Sirius will be the children or grandchildren of the people who left Earth. This transition introduces a set of problems that no amount of mechanical engineering can resolve. The children born aboard the ship did not choose this mission. They were born into it. They were raised by people who remembered sunlight and rain and open sky and a planet with billions of other humans on it. The generation after them will be raised by people whose entire lived experience is the ship. Their connection to the civilization that built and launched the mission will be a story, told by people who themselves only experience that civilization through other people's stories. The cultural and emotional connection between the crew and the mission's original purpose weakens with every generation. Not because people stop caring, but because the chain of personal experience connecting current crew to original mission rationale grows longer and more abstract. Sirius itself presents a destination hazard. It is a binary system. Sirius A, a bright, massive main sequence star about twice the mass and 25 times the luminosity of our Sun, orbited by Sirius B, a white dwarf remnant of a star that has already exhausted its nuclear fuel. White dwarfs radiate intensely in ultraviolet and X-ray wavelengths. The interaction between the two stars creates a complex radiation environment in the system. Shielding adequate for the interstellar void may be insufficient for close approach in a binary system containing a white dwarf component. Tau Ceti, at roughly 11.9 light-years, is a G-type star similar in spectral class to our own Sun, making it one of the more scientifically appealing nearby targets. At 10% of the speed of light, the journey takes approximately 120 years. This is the first rung where the voyage spans multiple generations with no ambiguity. The original crew is long dead before arrival. Their grandchildren are the ones who make landfall, or, more precisely, who enter orbit and begin assessing whether any of Tau Ceti's candidate planets are worth the name. 120 years of continuous ship operation. The Roman Republic lasted about 500 years. The United States as a constitutional republic has been in existence for roughly 235 years. Many powerful empires and institutions in human history have not lasted 120 years in recognizable form. A starship that needs to maintain its mechanical, social, and institutional integrity for 120 years is being asked to outlast, inside a sealed metal container with no external cultural reinforcement, an interval of time during which virtually every major human institution on Earth has historically changed fundamentally. TRAPPIST-1 sits at roughly 40 light-years from our solar system. It is an ultra-cool red dwarf with approximately 9% the mass of the Sun. The system is scientifically notable because it hosts 7 confirmed rocky planets, 3 of which orbit in the habitable zone. No other known system at a potentially accessible distance offers this many rocky planets in potentially favorable orbits. James Webb Space Telescope observations have begun characterizing the atmospheres of these worlds, with results so far suggesting at least some of the inner planets may have lost their original atmospheric envelopes, while the habitability of others remains uncertain. At 10% of the speed of light, the journey to TRAPPIST-1 takes approximately 400 years. 4 centuries. The Ottoman Empire lasted about 600 years. The Ming Dynasty lasted roughly 275 years. The gap between the first European settlement at Jamestown and today spans about 420 years. A starship heading to TRAPPIST-1 must maintain its operational integrity, its social coherence, its institutional knowledge, and its sense of mission purpose across an interval comparable to the entire history of European settlement of the Americas. At this distance, calling the ship a vehicle becomes a category error. It is a civilization. It must educate its children from generation to generation. It must govern itself without external authority, court of appeal, or the option to emigrate to a different community. It must resolve conflicts, manage resources, assign roles, and maintain mission commitment across at least 15 to 20 successive generations, none of whom had any say in whether the voyage began or continues. Birth rates must be managed with a precision no society on Earth has ever voluntarily accepted. Too few children and the population ages, skills gaps open, maintenance burdens accumulate on a shrinking workforce. Too many children and the ship's caloric budget, water budget, and atmospheric capacity exceed their design margins. Every child born aboard is not simply a new community member. Every birth is a resource allocation event whose downstream consequences cascade across decades. Vocational assignment raises ethical questions with no clean resolution. The ship needs specific numbers of people with specific skills in every generation. Reactor engineers, life support technicians, agricultural specialists, medical practitioners, navigators, fabricators, educators. If natural aptitudes in a given generation trend toward arts and philosophy, rather than technical fields, the ship's maintenance capability in the following generation is compromised. On Earth, career choice is considered a fundamental expression of individual autonomy. Aboard a starship, a generation that produces too many artists and too few engineers may eventually kill the ship through accumulated deferred maintenance. The psychological weight of being born into an unchosen mission is distinct from choosing to embark on one. The first generation accepted the sacrifices with eyes open. Their children were raised by people who could describe what Earth felt like. By the 4th or 5th generation, Earth is an abstraction, a historical event described in documents written by people who have been dead for centuries. The mission's rationale, whatever it was when the ship departed, may have become as remote and difficult to emotionally connect with as the motivations of ancient explorers are to us today. A community sealed in a metal container for 400 years will develop its own culture, its own mythology, its own values that diverge from the departure-era civilization in ways that cannot be predicted or prevented. This cultural drift is not a failure. It is what human communities do over time. The question is whether the drifted culture, whatever it becomes by generation 15, still possesses the will and the institutional capacity to perform the deceleration burn when the destination star finally grows bright enough to see clearly. Vega sits at roughly 25 light-years. At 10% of the speed of light, the journey takes approximately 250 years, 2.5 centuries of transit time, the distance from the late 1700s to today. The entire history of the United States as a constitutional republic does not fill that interval. The engineering survival requirements at 250 years are, at this point, almost secondary to the institutional and purposive ones. The mechanical challenges are severe and genuinely unsolved, but the deeper problem at Vega's distance is that a civilization that commits 250 years of its existence to a mission cannot guarantee that the civilization launching the mission will still exist in a recognizable form when the ship arrives. It cannot guarantee that the Earth the mission departed from will still be monitoring and caring about the outcome. And it cannot guarantee that the crew that arrives, separated from the departure generation by 10 or more generations of cultural evolution in total isolation, will still understand or care about the mission's original rationale. Polaris sits at somewhere between 320 and 430 light-years from Earth, the uncertainty reflecting genuine measurement difficulty. At 10% of the speed of light, the journey requires somewhere between 3,000 and 4,300 years. 3 to 4 millennia. The entire span of recorded human history does not reach 6,000 years in either direction. A starship aimed at Polaris must outlast every empire, every religion, every language, every nation, and every institution in recorded human history, inside a sealed metal container with a finite supply of replacement parts and a crew whose connection to the original mission stretches back more generations than separate us from the Bronze Age. At this duration, the engineering ceases to be the primary constraint in any meaningful sense. No material humans can manufacture has been tested for 3,000 years in a high-radiation, vacuum environment. No institution has maintained organizational coherence across 150 generations in isolation. The ship would need to be not merely maintainable across this period, but effectively rebuildable from the inside, replacing its own components as they fail across millennia, regenerating itself from its own material inventory as a biological organism regenerates from its own cellular machinery. The purpose problem appears at every rung above Alpha Centauri, but becomes dominant beyond Tau Ceti. Human beings can endure extraordinary hardship when they believe it serves a meaningful goal, larger than themselves. Missions acquire this capacity when the people on them share a conviction that the sacrifice is worthwhile. Remove that conviction, and the suffering that remains, the confinement, the radiation, the recycled air, the rationed water, the never seeing a sky, becomes unbearable in a way that no engineering solution addresses. A Starship crew that learns their mission has been rendered obsolete by a faster ship launched from Earth decades after their departure does not experience disappointment. They experience the collapse of the framework that has given meaning to every sacrifice they and their parents and their grandparents made. Why maintain the water recycler if the destination has already been reached? Why educate the next generation in reactor physics if the mission is already concluded? Why endure the accumulated hardship of transit for an outcome that was achieved without them? The psychological literature on isolated groups, from Antarctic winter over teams to submarine crews to remote expedition members, consistently shows that purpose loss is among the most destructive forces a small community can experience. It does not produce orderly philosophical adaptation. It produces depression, conflict, withdrawal from communal responsibilities, and in extremes, violence. A starship that loses its purpose does not peacefully transform into a community living for its own sake. It fractures, and fractures aboard a sealed vessel with no emergency exits are not metaphorical. They are lethal. Behind every conversation about when to launch an interstellar mission sits a mathematical problem that receives far less attention than it deserves. It is called the weight calculation, and it argues that for many targets, the rational decision based on expected future improvement in propulsion technology is not to launch now, but to wait, sometimes for a very long time. The argument works like this. Suppose propulsion technology improves at a consistent rate, such that a ship built 10 years from now can travel twice as fast as a ship built today. A ship launched today toward a star 40 light-years away at 10% of the speed of light takes 400 years to arrive. A ship launched in 10 years at 20% of light speed takes 200 years. Despite launching a decade later, the second ship arrives 190 years earlier than the first. The crew of the first ship, still in transit in year 11 of their 400-year voyage, has already been overtaken in terms of arrival time by a mission that hadn't launched yet when they departed. More formally, physicist Andrew Kennedy showed that for any consistent rate of propulsion improvement, there exists an optimal departure date that minimizes the sum of waiting time and travel time. For many realistic targets at realistic rates of improvement, that optimal departure date lies in the future. Launching before it means being overtaken. Waiting for it means a faster, more efficient mission arrives first, making the earlier launch redundant. The implication for any specific interstellar mission concept is uncomfortable. A ship launched today based on the best available propulsion technology may be overtaken by a mission launched a century from now using technology that does not yet exist. The crew of the first mission may receive, in year 100 of a 300-year voyage, a transmission informing them that a second ship launched decades after theirs has already arrived and begun operations at the destination. Their entire voyage, all the sacrifice, all the maintenance, all the generational commitment has been rendered redundant by a civilization that simply waited and built something better. This is not purely theoretical. It describes the ordinary trajectory of technological progress. The first transatlantic telegraph cable was laid in 1858 and failed after a few weeks. The second, more successful one came in 1866. Early transatlantic flights took more than 33 hours. Modern flights take 7. In every domain of technology, early implementations are eventually superseded by later ones that are faster, cheaper, and more capable. There is no reason to expect propulsion technology to be exempt from this pattern. A crew aware of this calculus lives with a particular form of existential uncertainty. They know that improvement in propulsion technology may be occurring on Earth. They know that communications from Earth arrive with ever-increasing delays. They may, at some point, receive news suggesting that a faster mission has been planned. They cannot know from inside a transit lasting decades whether that faster mission was launched, whether it succeeded, whether it has already arrived. The obsolescence problem is distinct from, but related to the purpose problem. Even if the crew maintains complete commitment to the mission's original goals, they may find that those goals have been achieved by someone else before they arrive. The destination may not be empty when they get there. The scientific questions the mission was designed to answer may already have been resolved by faster probes launched decades after them. The new world the mission was designed to reach may already have a settlement established by a mission with better propulsion launched years later. Arrival becomes not the culmination of the mission, but a coda to a story that was concluded without them. And then there is the scenario where Earth goes silent. Communication from Earth arrives with delays measured in years or decades. There may come a point in a multi-century voyage where transmissions from Earth stop. The crew does not know if Earth lost interest, if the transmission infrastructure was dismantled, if something catastrophic happened to the civilization that launched them, or simply if the signal has degraded beyond detectability. The silence may lift, it may not. The crew continues the voyage in either case, because there is no other option, maintaining systems and producing children and transmitting their own signals, into a void that may no longer contain anyone listening. That is the final form of the purpose problem. Not that the mission becomes redundant, not that a faster ship overtakes you, but that the civilization that gave the mission its meaning simply ceases to be there. The Starship becomes the last remnant of a civilization that no longer exists, carrying the memory of an Earth that may be gone, aimed at a destination that the dead would have wanted it to reach, crewed by people whose only connection to the origin is the story they were born into. Suppose the ship survives. Suppose every engineering challenge described in this conversation was solved by extraordinary design and diligent maintenance. The water recovery system held near 100% closure for the full voyage. The carbon dioxide scrubbers were regenerated and replaced from onboard stock across decades without atmospheric composition drifting outside safe limits. The reactor ran with intolerance, its fuel carefully managed, its coolant loops maintained without a catastrophic failure. The agricultural system produced adequate calories and nutritional diversity across every generation. The radiation shielding, active or passive or both, kept cumulative crew doses within ranges that allowed the population to remain functional. The spare parts inventory was managed carefully and augmented by fabrication when possible. The institutional knowledge was transmitted from generation to generation without critical gaps. The governance structure held against the social pressures of multi-generational isolation. The propulsion system, dormant for the full cruise phase, fired correctly when commanded for the deceleration burn. The ship arrives. It decelerates successfully. It enters the destination system intact. The crew is alive. Every system is still running. The mission, by every mechanical and biological measure, is a success. Now, ask the harder question. Does anyone aboard still understand why they came? And does anyone on Earth still know they left? These are not sentimental questions. They are engineering requirements in the most fundamental sense, because a mission that arrives without the crew understanding its purpose and without a civilization capable of receiving its findings has not succeeded. It has simply relocated. The ship has traded one sealed environment for another, slightly closer to a different sun, with no more context for its own existence than it had in the middle of the transit. The stars are patient. They will burn for billions of years. They do not require humanity to visit them. They offer no reward for the attempt and impose no penalty for not making it. They simply exist at distances that test the absolute limits of what machines, bodies, and civilizations can sustain. The question this entire conversation has worked toward is not whether a starship can be built. Given enough time, enough resources, and a civilization with the will to commit to projects whose completion lies beyond the lifetimes of everyone who begins them, some version of a starship will almost certainly be attempted. The question is how long every system aboard can survive simultaneously, interacting, degrading together, under the care of a crew that has no backup and no external support, and no option other than to keep every system above its minimum threshold until the distance shrinks to zero. Right now, there are 5 spacecraft on trajectories that will carry them into interstellar space. Voyager 1 and Voyager 2 have already crossed the heliopause. Pioneer 10 and Pioneer 11 are following. Contact with both long since lost. New Horizons is moving outward through the Kuiper Belt. All 5 are tiny, crewless, and coasting with no propulsion. None will pass near another star for tens of thousands of years. They carry no life support, no food, no water, no crew. They are the most distant objects humanity has ever placed in the cosmos, and they are incomprehensibly simpler than a real starship. A real starship is not defined by its top speed. It is defined by whether the air stays breathable in year 60, by whether the reactor still runs in year 100 through 50, by whether the crew in Generation 8 still possesses the knowledge and the will to maintain systems their great-grandparents installed, by whether the hull holds against decades of dust at velocity, by whether the governance structure resolves its crises without fracturing the community it needs to keep the ship alive, by whether the deceleration burn fires at arrival after a dormancy spanning the careers of every person aboard. A starship is not a faster rocket. It is a machine that must outlast its own degradation, preserve its own purpose, sustain its own civilization, and carry a fragment of what it means to be human through a silence so deep and so long that the civilization it departed from may not exist by the time it arrives. Every critical system aboard is a clock counting down. The only question that matters is whether every one of those clocks can be kept running long enough for the distance to shrink to zero. The stars are not going anywhere. The only thing that wears out is everything aboard the ship trying to reach them. That is what a real starship demands. Not faster engines, not better fuel, not more thrust. A machine that can survive being alone long enough to matter. There is one more dimension to the challenge that rarely enters the engineering conversations and almost never enters the popular ones. It is the question of what the starship's arrival actually means, not mechanically, not institutionally, but in terms of what it delivers to the civilization or the community that made the journey. When European explorers crossed the Atlantic for the first time, they returned. The knowledge they carried back fed into the civilization that had sent them. The voyages changed the world because the information they gathered could be brought home and acted on. An interstellar mission does not have that option in any immediate sense. The data the ship collects at arrival is transmitted back at the speed of light, which means it arrives at Earth 4 years after the ship does for the nearest target, 40 years after for TRAPPIST-1, and 300 years after for Vega. By the time that data reaches Earth, no one who authorized the mission is alive. The civilization that receives it may not be able to do anything with it for a generation or more, simply because of the time required to interpret and act on it. The crew that arrives cannot return, not on any timescale that connects them personally to the civilization of departure. An interstellar crew arrives at their destination and stays. If the destination is habitable, they establish whatever presence the ship's resources and the planet's conditions allow. If it is not habitable, they study it from orbit and transmit findings home and make the best life they can inside the ship, indefinitely. Either way, the mission's conclusion is not a return to Earth. It is the beginning of a permanent settlement at an incomprehensible distance from everyone and everything the mission originated from. This permanence is almost never stated directly in conversations about interstellar missions, because it makes the decision to launch a mission sound like what it actually is: a permanent, irrevocable separation of a community of human beings from the rest of their species, across a distance that makes any kind of real-time connection impossible and any kind of physical support permanently unavailable. The crew is not being sent on a journey with a destination and a return. They are being relocated to a place that has never seen a human being, from which they will never come back, surrounded by systems that must never fail, with no one to call for help. That is the proposition that every serious conversation about interstellar travel is actually making, stripped of the language of adventure and exploration and species expansion that usually surrounds it. It is the proposal to cut a piece of humanity off from the rest and send it across the void, forever, sustained only by the machines around it and the culture within it, to whatever the universe happens to have placed at the other end of the distance. The people who accept that proposition, if they ever exist, will be among the most extraordinary human beings ever born. Not because they are braver than others, though they will need to be brave. Not because they are more competent than others, though every one of them will need to be competent at multiple things simultaneously, but because they will have accepted, with full understanding, a condition of permanent isolation from the rest of their species, permanent dependence on technology that has never been tested at the required duration, and permanent uncertainty about whether the destination, when they arrive, will be worth having come. Understanding that the ship must first survive to make any of that possible, that survival is the foundation beneath every aspiration and every sacrifice, is not pessimism. It is the precondition for taking the mission seriously. Because a mission that does not survive is not a brave attempt. It is a tragedy. And the tragedy is avoidable if the survival problem is treated with the same seriousness that the propulsion problem typically receives. The correct question about interstellar travel is not how fast. It is how long can everything aboard keep working, and then long enough to matter.